Okay, this is the basics of calculus, the mathematics of change. Going up a hill and down into a valley and then back out. At the bottom of the hill, we are looking up as high as we can. Once we get to the top, we're looking even with the horizon. So if we're looking up as high as we can, we're going to note that by a high mark on the second graph. The point at the top, where we're even, we are neither looking up nor down. So that we mark as a 0 point down here. And again, when we're at the bottom of the hill, we are going down as fast as we can just before we start slowing down to move in the direction of the horizon. So we're going to mark that by a low point, because we're moving down as fast as we can. And so on and so forth. The bottom of this one, we are neither looking up nor down. And over here, we are looking up as high as we possibly can, which correlates to this spot. So if this is our height, this is the time, then this is a graph of our height according to time. This, being derived from that, is the derivative of this. This is a change in height according to time, which is the vertical velocity according to time. So the velocity starts off high, goes down to 0, goes down to negative, goes up to 0, and back up to the highest point. So down here we have the second derivative, which is taking the same thing. This is looking even with the ground, so that is neither above nor below ground. This here is at the ground level, but we are looking down as hard as we can. So that is a low point, and so on and so forth. That's calculus. This is physics. If your height is in meters, your velocity of your height is in meters per second, your acceleration is in meters per second squared. And that's the basics of calculus and physics. This is Hubble's graph. He viewed that the further out you go into the universe, the stars are going faster and faster. This is velocity, this is distance. But distance being in light years, this one is so many light years old, this one is even older, and this one the oldest. So how is this acceleration? Acceleration is not change in velocity over change in distance, it's a change in velocity over time. So out here we have the theoretical Big Bang, or the beginning of time, which is out here, not here. So time is actually going backwards on this graph. So I think Hubble needed to do one more step, convert this to a time graph, in which case you would see the fastest stuff first, and it would actually be going down to the present day. Now, this graph also does not represent the Andromeda Galaxy, which is actually below this here. We are actually getting closer to Andromeda. There are stars out in the universe, or galaxies rather, that we can see are colliding. So not everything is moving away from everything else. Some things are colliding. So if we go backwards in time, we see a deceleration of the stars of the universe. Okay, most of us should remember the DIRT equation, distance equals rate times time. If we got our velocities either accelerating, constant, or decelerating, we'll say the one in the middle is traveling at a constant speed, the one on the right is traveling at an accelerating speed and decelerating speed. Using DIRT, we know the measured distance, we know the measured velocity, which is the rate. We're assuming that time is approximately 14 billion years ago. So if we could extrapolate from their current velocity, their current distance, and the total time that they've been traveling, they should all come back to the same point at the same time. If it is decelerating, it won't go back quite as far because previously it was going faster, now it's moving slower. If it's going at a constant rate, then everything will line back up to the origin at the same time. If it's accelerating, that means it's moving faster than it was when it started. So if you extrapolate back, it should go back further than the beginning of time. And I think that's how we can figure out whether things are accelerating or not. Because even turning that around doesn't guarantee that we are accelerating. So what my interpretation means is that we do not have dark energy, or at least not as much as we think. Since these things are not flying apart, they are actually slowing down. I have another theory which might eliminate some dark matter. I understand dark matter was conceived of because the stars traveling around the galaxy don't seem to be going at the right speeds. And I think because of our twisted view here, I can explain some of that dark matter. On the too much information portion, this is a model of a hydrogen atom, proton and electron. In an MRI, as far as it was explained to me, when you put this into a magnetic field, you can actually pump up the energy of this electron into the next layer. So it's kind of like this. The electron is most comfortable at the bottom of the pool, but then we give it some energy and it floats to the top. But there's nothing below it, so it's not stable, so it falls back down. When it falls back down, it releases energy in the form of radio waves, and therefore we can take a picture of how dense the hydrogen is. So hydrogen being a major component in brain tumors, we can scan your brain and see a brain tumor like they did in me. This here is just Einstein's E equals mc squared. It's on here just to point out that energy and mass are the same in proportion to the speed of light squared. So mass is crystallized energy. And that looks like it.